Osmotic pressure. So osmotic pressure, you first have to understand osmosis. So osmosis involves a semi-permeable membrane and involves a separated set of solutions. In this case, one is just the pure solvent, and on the other side of this semi-permeable membrane is a solution. I have solute particles and solvent particles. So as the name suggests, semi-permeable means that only some things can get through, in this case on the basis of size. So you can see here that the solvent particles can pass through the gaps, but the solute particles can't. Now, the solute particles would like to diffuse out because they would like to increase their entropy. This is a very entropy-driven process. So because the solute cannot spread out, the solvent moves in to dilute the solution out, increasing entropy, because now I have a greater volume in which the solute particles can move around. They have more possible places they can be. So in order to increase the entropy of my solvent, you have a movement of of my solute. I increase it by moving solvent particles in there. A more concentrated solution means that the solvent has to move in, more of it has to move in, and that degree of how much it wants to move in is called osmotic pressure. What happens, you'll see, is that as the solvent moves in, my volume rises, and so this will cause an increase in volume. If this is a cell, then the amount of solvent going in could be to the point where it actually bursts the cell. If it's a plant cell, because you have the cell wall around it, as the water moves in, the cell wall becomes rigid and it becomes like pumping a tire full of air. That's why plants unwilt when you put water on it. Wilted stage is like, and then when I add solvent, water, the water goes into the cells and it increases the pressure and the plant perks back up. It's also a way to explain the movement of sap in trees as it goes from the roots all the way up to the leaves. So how do I calculate this? So a liquid and a gas are both considered fluids. Are all fluids. These are all fluids, and so they behave in the same manner. And so I can actually use the same equations for gases, like the ideal gas law, with liquids. There may be some exceptions that I have to, some little provisions that I have to do in order to account for the fact that you have IMFs, but for the most part, you can think of them in terms of fluid dynamics. So if I take the PV equals nRT, which is my ideal gas equation, and I recognize that N over V, moles per liter, is molarity, I can rewrite mine in terms of osmotic pressure to be pressure is equal to mRT. So to distinguish, we use a capital pi as osmotic pressure, so pi equals mRT, and because I'm using the same R value, it's going to be 0.0821 liter atmospheres over moles Kelvin. So my first example is calculate the osmotic pressure of a 6.2 molar solution at 27 degrees Celsius. Just a reminder, anytime you use R, you have to use Kelvin. So I'm simply plugging it into my pi equals mRT, molarity, times my R value times temperature converted to Kelvin, and I get 152.7 atmospheres. Example B, sap in a maple tree is 3% by mass solution by sucrose. The molar mass of sucrose is 342.3 grams per mole. If the density of sap is about 1.01 grams per milliliter, 1, calculate the molarity of the sap, calculate the osmotic pressure at 25 degrees Celsius, and if 760 millimeters of mercury, which is 1 atmosphere, is equal to 10.184 meters of water, how high up the tree can the sap rise? So if you're looking at A, I have 1 liter of sap. I convert to milliliters, so I can get to grams. Then I find the molar mass, multiply this by the percent of this 1 liter that is actually sap, sucrose, and I find that the molarity of my sap is 0.0886 molar. If I plug this into my pi equals mRT, I find out that this molarity of my solution will exert an osmotic pressure of 2.16 atmospheres, which is enough to move the sap up the tree 21.99 meters. That's fairly high. We're talking about like a 65-foot tree there. So this is the major factor in the springtime because there's no leaves on the tree. So before the leaves come out, the sap that has been stored in the ground so that it doesn't freeze is rising up to the top and transporting sugar there so that those cells in the buds can transform themselves into leaves. And in order to do so, it has to have a high enough molarity in order to be able to rise to the top. The higher the tree, the more concentrated the sap has to be. And the colder the temperature, the more concentrated the sap has to be in order to generate the osmotic pressure to go up the tree. This is why we tap trees in the early spring. That's when the sap is rising. It's when the concentration of sucrose in the sap has to be the highest. And the taller the tree that you tap from, the more sugar there will be in that sap. So we don't tap small trees for two reasons. One, it's going to kill the tree, and that's not good. But two, it's not going to give you as much bang for your buck as if you get one from a more mature tree. Interestingly enough, plants are able to change the molarity of not just the sap, but also their cells in the roots. So one of the things that you can see in the wintertime, in the early spring, is that when there's still snow on the ground, this early spring ephemerals, the bulbs that are coming out, will often have a patch of melted snow around them and just dirt. What's happening is that they are exuding out solutes into the soil to raise the melting point of the soil so that you can get liquid water so that it can start to germinate and start to grow. So plants have that ability to control not just the solute concentration in their own cells, but also the solute concentration in the soil around them to maximize water movement and sap movement both in and out of the plant, to change the freezing point of the soil around the plant, and also to allow sap to flow up to the leaves.